Still in chapter or unit 6, but moving right along, aren't we? Let's see, we've done this, and we worked on the law of cosines last time. Now we're going to find the area of a space. There's two ways to do this. We're either going to use Heron's formula, or we're going to apply some area formulas for finding area. The very last session we will do in Unit 6 will be some real-world examples. Possible and impossible conditions in triangles. Determine if the values given are even possible. If we have one side that's 10, another side that's 12, and a third side that's 25, can we form a triangle with this? Well, imagine it. Here's C, and now I'm not even going to try and do a triangle yet. So I've got this, which is 25 units long. Let me change colors. And then I've got, okay, so here's my C. Now I'll do B, which is 12. 12 would be almost halfway, wouldn't it? Almost halfway. And then we've got A, and A is 10 units long. Well, there's no way that you can put those together and make a triangle. Pretty clear that you can't, isn't it? If you have two sides which are less than the third side, then you cannot make that triangle. Well, how about this one? How can we figure this one out? It seems like it might be possible. We've got beta of 51. So right here, we know what this is. Let's write it in. So we've got 51 degrees here. The side opposite we don't know, but we do have A, which is 10, and C, which is 5. So what is the situation we have here? It's side, angle, side. How does that work out? Just fine. And the next one. See what we've got here. We've got alpha, which is 50. We've got opposite alpha, which is 2. And we've got B right over here, which is 10. So in this case, we've got side, side, angle. Side, side, angle. And what do we know about this? This is the ambiguous case. So there's a potential that it is not possible, as well as the potential that there's a single triangle or two triangles that will work for this. Let's check this one out. If we try to figure out what sine of beta is, we're going to find it is greater than 1. So how did I even get to this? I would do the law of sines. I'd get a relationship, and I would then go for beta, because the second side that I have is B. That's when I would discover that we have an impossible ratio for sine. Let's look at this last one. A is equal to 5, B is equal to 6, and C is equal to 8. For this one, I can go right back into this kind of thinking to see whether or not it would be possible. 5 plus 6 is greater than 8. 6 plus 8 is greater than 5, and 5 plus 8 is greater than 6. I don't see any problem with that, do you? No side is greater than the sum of the other two. We're going to use trig to find the area of a triangle. Well, we've known for a long time what the area of a triangle is, haven't we? We know the area of a triangle is 1/2 of the base of that triangle times its height. 1/2 of the base of its triangle, of the triangle times its height. So we're going to look at this triangle right here. Just this little right triangle. And focus in on that. And we can say that the area of the whole triangle is still 1/2 times the base. And let's say we know what B is. And let's say that we know what gamma is. And let's say we know what A is. So if we have side, angle, side, side, angle, side, then we can use this because our height, here's our height, height can be represented by the opposite height over hypotenuse. Let's write it out. The sine of gamma equals the opposite, which is height, over hypotenuse, which is A. So we can say that height equals A times sine of gamma. Here it is simplified. And we worked on. But we could have used A and C and beta. Or we could have used B and C and alpha. Woof! Find the area of a regular. Oh, remember what regular means in geometry? It means that all sides are congruent, doesn't it? And in a polygon, it also means that all these angles are also congruent. Find the area of a regular octagon inscribed inside a circle of with a radius of 9 inches. So one of the things we know is that this triangle that we see here is being repeated here, here, and so forth. It's being repeated 8 times. If we can find the area of one triangle, so area of this triangle, this little green triangle, if we take that area, multiply it times 8, we will have the area of our octagon, right? So let's focus in on this. What have we got? Well, if we called this A, and we called this B, and we called this C, this theta would be gamma in our formula here, and we'd use this for our triangle. Well, we do know what A is. A is equal to 9. B is equal to 9. And gamma is equal to, seems like a question, might be hard to answer, but let's think about it. If we go all the way around, we've got 360 degrees. And an octagon will break up into central angles that are identical to one another. And those will be, let's figure it out, 360 divided by 8. 360 divided by 8. It's going to be 45. Ooh, isn't that nice? We love 45. So these are 45 degrees. Gamma is 45 degrees. What is the sine of 45 degrees? Now, you know, this is one of our special angles, our familiar angles, our friendly angle. So we already know what this is, right? We can look on our unit circle, or perhaps you just can remember it from thinking about this triangle. This was 1, 1, and the square root of 2. If you convert it into a unit circle, you divide everything by the square root of 2. So even if your unit circle isn't handy, we can figure out what this is, 1 over the square root of 2. Anytime you're dealing with area, that kind of dimensional question, we actually are going to need to convert this into decimal. On 1 divided by the square root of 2 gives us a decimal of 0.7071. All right, 0.7071. So now when I put this formula together, I've got the area of this green triangle is equal to 1/2 A times B, which will give me 81, times the sine of gamma, which we have determined the decimal value for. Let's pull back our calculator, and we've got our sine of gamma, and we're going to multiply that, multiply times 81, and then divide by 2. 28.6. 28.6. Oh, I do have units. If I didn't, I'd say units squared. So we're going to say inches squared times. So I got the area of my green triangle, and now I have to multiply it times, what do we say, times 8 for an octagon, of course. Yes! All right. What is a semicircle? Let's start with something we are very familiar with. A semicircle is a half a circle, right? So what would a semi-perimeter be? That's right. It will be half of a perimeter. And we're actually going to use that concept here. we're going to say S is a semi-perimeter. Now we're used to thinking of S as meaning side. Not now. Remember how in mathematics context makes a huge difference. When we go into statistics, we'll talk about context a lot. So here we've got Heron's formula, which uses the semi-perimeter. Heron's formula tells us that the area of a triangle, if we know all three sides, we can calculate without having to know what the height is, without having to know what any of the angles are. Now we could skip Heron's formula and we could still figure it out because we know how to solve this problem, and we could find one of these angles and then we could go back and do it the way we find the area of a triangle with sine. But this is going to be much quicker for us because we don't have to go into any of the trig functions, do we? Sometimes that might be nice. So we're going to find what is the semi-perimeter first. So we're going to add 13 plus 15 plus 18. Our semi-perimeter is half of 46, which would be 23. So let's write that down. S equals 23. Now we go into, so I don't expect you to memorize this. I will give it to you as you need it. So our area is going to be the square root of 23, and then we multiply that times 23 minus whatever a is. We're going to say, yeah, it's minus 13. So 23 minus 13 would give me, and then 23 minus b, here's my b, would give me 8, that's right, and 23 minus c, 18, 23 minus 18, okay, there. So now we just bring the calculator over and we do all the calculation. Whoop, what did I do? We do all the calculations with this. So turn it on. 23 times 10 would be 230. And here we've got 8 times 5, which is 40, so I'm just going to say times 40. And now I'm going to take the square root of that by saying raised to the power of 1. Oops. I forgot I have to use my parentheses. So that would be the square root. 95.9. So this equals 95.9. And this time I don't know what the units are. So I'm going to say units squared. Let's see how that matches with an earlier work by me. Yes. Okay. So now right out of your notebook or your workbook, we've got example 19 and example 20. Let's see which way we're going to go with these. This one, we can use SAS, can't we? We haven't got the side opposite, but we've got the two adjacent sides, so we can use this one. And which of the variants are we going to work with? we've got B and C and alpha. So we go for this one right here. This is the one we're going to work with. What is the sine of 68 degrees? Let's make sure we're in the right mode. We are not. We'll put ourselves in degree mode, and now we'll find the sine of 68 degrees. Okay, 0.9272. So our area is going to equal 0.9272, and it's going to be 1/2 B times C, which would be 40. So basically 20 times sine times 20, 18.5. And we don't know what the units are, so we say units, whoops, don't forget your I, squared. We didn't have to solve the whole thing, did we, to find the area? And how about this one? Well, we haven't got the opposite side, but we've got the two adjacent ones. So again, we'll be able to use SAS. This time, we've got beta, and we've got A and C. So this is the one we're going to use now. And we'll start by finding the sine of 14.3. We remember doing this problem, don't we? At least I do. Sine 14.3. Okay, so it's 0.24, basically 7. And we're going to multiply it by 6 times 25 and then divide that by 2. So that's the same as multiplying by 75, isn't it? Boy, I hope so. So we have an area here of 18.5. 18.5 units squared. Yes, he must have chosen them purposefully to show us that, don't you think? Very close in area. Here's another example. Ho, 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 ho. Well, we've seen these before, haven't we? Now this time we're going to have to use Heron's formula. So here we are, SSS, and we have to find our semi-perimeter. S stands for semi-perimeter. We add these all up. Okay, did I do that right? 28. So the semi-perimeter is going to equal 14. So what I get for product here is 14 times, I'm going to subtract A from 14, then I'm going to subtract B from 14, and then I'm going to subtract C from 14. Okay, turn this on. 14 times, this amounts to 70, right? 35 twice. And then we'll take the square root of that. And our answer is 31.3. 31.3 I'm never patient enough with a point. 0.3 units squared. On this one, what will the semi-perimeter be for this? Well, the perimeter would be equal to 15,000, wouldn't it? So half of 15,000 is 7,500. So my area is going to be my semi-perimeter, then semi-perimeter minus A, semi-perimeter minus B, and semi-perimeter minus C. All right, so we get our calculator over here, and we'll say 7,500 times 1,500 times 3,500 times 2,500. Yeah, I got it all. And notice it's put it into scientific notation. That doesn't bother us at all. We're going to find the square root of that. Okay, look at that. Ooh, that's the area. Well, this would be something maybe if we were looking at a rectangular plot of land or something. So we've got, wow, it's so huge. 9 million. I'm just going to round it to the nearest thousandth. 9,922,000. Woo-wee! 9,922,000. And again, it's units squared. How about this one? What would be the quickest way to get there? In either case, you're going to have to get this figured out. It's going to be a multi-step problem, isn't it? We're going to first, I love the law of sine, so we'll just go ahead and figure that. The sine of 31 degrees over 22 will give us the law of sine ratios that we want to use. So sine of 31 divided by 22 gives us a ratio 0.02341. 0.02341. I can figure out what my beta is with sine beta over 9, which is going to equal this ratio. The law of sines is so neat. So the sine of beta will be this ratio times 9. And I'll find out what beta is by putting that ratio into arcsine, 0.21069. .16. oof, 12.16 degrees. Okay, so what will gamma be? We'll add 31, and we'll find the difference with 180. 136.8. 136.84 degrees. Now I could use SAS to find the area. Let's do it. I'm going to, which one am I going to use? I've got A and B, and now I've got gamma. So this is the one I'm going to use. I'm going to find the sine of 136.836 of that angle. The sine is 0.6841. The sine of this is 0.6841, and I'm going to multiply that times 22 times 9, and then times 1/2. So times, I shouldn't cover up the numbers, times 22 times 9, and then I'll divide by 2. That's the same as multiplying by 1/2. And I'll have my area of 67.7. So area of this triangle is 67.7 units squared. Let's do another one. This is similar, isn't it? Well, I'm going to leave this one to you. For you in class, you can use the same approach. And also in class, we'll do homework problem number 5.